Good morning, everyone, and welcome to the third Core Tech webinar that Brainome is putting on to share the insight into the mathematics and the algorithms and the applications of how our Dimensions software works. Today we have Gerald Friedland, who's our CTO, who's going to be presenting. We're in the middle of two webinar series that are running in parallel. Today is Core Tech 301, where we're going to summarize the mathematics and the algorithms and then look at some really cool examples. And then we're also in the middle of a parallel webinar series on the benefits and applications of the software. This week on Thursday, our topic is working with time series data. You can find all the information you want about the webinars, and you can sign up for any or all of them down at the URL at the bottom of the page here. I'd like to invite you to put your questions into the Q&A channel as we go through the webinar today. Gerald will be talking for just a short period of time, and then we're definitely going to have plenty of time for Q&A at the end. So if you could just type your questions into the Q&A channel, we'll make sure that Gerald addresses them before the end of the webinar. Gerald is the CTO at Brainome, and he's also teaching as an adjunct professor at the Electrical Engineering and Computer Sciences Department at UC Berkeley. Before that position, he had been with Lawrence Livermore National Lab, and prior to that, at the International Computer Science Institute in Berkeley. His work focuses on signal processing and machine learning. He's published more than 250 peer-reviewed articles in conferences and journals, and he's also written 3 books. Gerald received his doctorate summa cum laude in computer science from the Free University in Berlin in 2006. So with that introduction, take it away, Gerald.
Thank you very much, Lynn, and thank you everybody for joining today. And this is the 301 seminar, and if you've been to 101, 21, you see there in series. However, what I want to do start a little bit with just repeating or sort of remembering what was introduced in the previous 2 seminars, and then this seminar will concentrate solely on an example that we run through where we see these different measurements. And just as a quick reminder, so we discussed 2 seminars ago that this is the generic workflow for machine learning, and it mostly focuses on accuracy. And usually it works this way: you have some data and you split it into training and testing, or training and validation. And then you choose a machine learner of your choice, often based on fashion or ideology or what you feel comfortable with. And you take that machine learner, build a statistical model or a non-statistical model, a model in general. And then you take this model, apply it to your evaluation data. And if the accuracy is high, you measure the accuracy against the ground truth. If that accuracy is high, you say, this machine learner works, I'm happy. And then you hope that obviously it'll work, in production and for the rest of forever for data like this. And so this is the standard process as we have it right now. So basically we have accuracy, we have sort of just really counting the number of correctly classified instances divided by the number of instances, which is 100, which is when you take it by 100 as in percent. And generalization is basically just measured as the same as accuracy, except on that holdout test set or validation set, as I meant. And so these are the major 2 measures. And then often nowadays people talk about model complexity, which is kind of often just referred to as the number of layers in a deep learner. And of course, the more layers, the deeper, and the deeper, the better. And or the number of parameters, where it's basically the more, the better. And, this GPT-3 model has 100 million parameters, so it must be good, okay? We discussed in the last 2 seminars that is obviously bigger is better is not always true. But most importantly, and also discussed in the last 2 webinars, that these measures, all of these that you see here, are all after the fact, after you build a model. And what Brainome does is it gives you measures that you can use before you build the model, or also to choose the model that you're going to build based on the data that is put in. And so obviously we do measure accuracy, but we also actually explicitly measure generalization. We measure what we call the memory equivalent capacity, and this was for model comparison, for detecting overfit, and also for detecting data drift. We measure what's called capacity progression, and we measure what's called risk of overfit, and we also measure bias. All of these things can be measured, and with the exception of bias and accuracy, they can be estimated before the model is built, and obviously generalization and memory equivalent capacity and overfit detection, all of these can also be measured after the model is built as an exact value, which helps you understand how good your model is, especially if you want to compare to other models you've built, or to models you've built based on different data, and so on and so forth. And again, sort of just as a quick review, there's a lot of value propositions that come with this product. And one is, first of all, when you have enough data based on the capacity progression, when you have the right features based on, you want the smallest model, when you're overfitting because we tell you, what the rules are that you learned, because often our models are super small and you can just look at them, and when your data drifts, because if your parameter count like jumps up or jumps down, just because you added a little bit new data, then something has dramatically changed. So this is, I went through this really quickly because this is basically core sort of 101 and 201 seminar described this, because what I really want to concentrate on is actually showing you how these measurements work in practice, how you can actually use them for your own good on a data set that we will understand first, and then go through it in detail, sort of how you actually productively work with those measurements. So let me switch my screen to, so this is the Brainome.ai website, which has a dimensions demo. So all you do is you go on demo, and we'll just use the demo for now for everything we do. And you can upload your own file, but for the demo right now, we use a data file it's the Titanic data set. So the Kaggle Titanic data set is a name in data science, but really what it just is, and we can take a look at here in the sort of the quick view that we have inside dimensions. It's really just a passenger list of the passengers of the Titanic. And yeah, the Titanic is obviously we talk about the historic Titanic that collided with an iceberg and sank. And the question is obviously, so here's a passenger list which has sort of an ID, the passenger class, which is the cabin class, then the names, the gender, the age, how big the family is in terms of siblings, how big the family is in terms of kids of that person or of that passenger, some ticket number, which seems to be quite random and not normalized as it would be today, because no computers were used. The fare, which like in pounds, how much was paid for the ticket, which is also very interesting because it varies greatly. It's a factor 10 here between the first and second passenger class. It's third passenger class. Then the cabin, sometimes multiple cabins, right? And then we have a code of in which port was embarked. And then the most interesting thing, which is the actual task, is a flag whether that person survived the disaster or not. So it's basically survived, yes, no, no, yes, no, yes, no, yes. Okay. And the question in the Kaggle task is, can we build a predictor such that based on, the passenger list and the survived yes, no, we could predict, for another part of the passenger list, the survival yes, no, and if so, with what accuracy. Okay. And so if you have a task like this, I would be immediately suspicious, right? Because the Titanic was a big disaster with many people dying and sort of ingrained in history. But if we would be able to predict with 100% accuracy who survived based on, I don't know, their name or their passenger class, this would be even a bigger scandal than it was. So we can already predict that 100% accuracy will not be the case. So this makes this data set also very interesting because we want to see sort of what the major factors are and what the best case prediction could be based on those major factors rather than just going for highest accuracy. So let's do this. So what Brainome gives us here is we have this data set, and the first thing we just do is we press the button for measure, and then it's measuring. And as it's measuring, This will take a couple of seconds. We get all these results. So we scroll down a little bit and we get all the measurement results. And these are all, or most of the measurements that I was sort of introducing earlier. First of all, we do very simple things like we have 891 instances in this. As you see, there are a couple of passengers that are not part of the list because they're held out set, they're the validation set. You have 11 attributes, 2 classes, survived, not survived. And in this particular subset, 61.62% didn't survive. And so basically the point is if I just said not survived to all of them, the best guess would be already 61% accurate. And of course, we are out to beat that. So these are just standard measures. But the next thing comes in, okay, so now let's calculate memory equivalent capacity for a decision tree and for neural networks. So the question is, would if I learned this, how far away am I from just memorizing the passenger list? And so it turns out if I use a decision tree, then I would still use 419 parameters to try to predict this. And for neural network, it would only be 118 parameters. And that's actually good because the decision tree seems to be only a factor 2 of, in sort of savings from instances to parameters. And neural network seems to generalize a lot better to about factor 7.5. So this estimate here is obviously an estimate. It tells us maybe we should use neural networks. Now, the other question is, in general, do we have enough data points? So what we do is we calculate what we call the capacity progression. And the capacity progression just gives us the number of decision points of an optimal, non-existent perfect machine learner, and tries to figure out, okay, so if I give it 5% of the training data, 10% of the training, 20%, and so on, how many decision points do I need? And the idea of this curve is, if I can extract a rule with a perfect machine learner that doesn't exist, then what happens is this curve should flatten, right? So it goes up and then it flattens out because once I have the rule, I don't need to add any data anymore. And if I cannot extract a rule at all, it would like completely sort of diagonal. It would look like, as I add more data, proportionally more parameters need to be added in my model because all we can do is memorize. Now, every real data set will be in between the two extremes, right? So this is a real data set. So what we see here is it kind of goes up linearly and then stops and then goes up a little more and then stops. And what it tells us is that a little more data would probably help. Now, we don't have more passengers on the Titanic. So for here, we have to take what we get. And unfortunately, it means we don't really know. It's kind of really in the middle between the two. So maybe enough data to generalize, maybe not. Now, another problem is if we now look at overfit risk. So overfit risk is determined by the fact that there's topological issues, right? So neural network, for example, if you just one parameter off, then you have to add a whole neuron, and that whole neuron adds a bunch of parameters, and then is also connected to an output neuron at least, which then adds more parameters even. And so that makes neural networks more prone to overfit because there's the structure to them. The decision tree, even though it would have it would have a lot more parameters and less generalization, it doesn't have that high of a risk of overfitting. However, as you can also see from the coloring of the graph, when it goes to green, yellow, red, if you're close to red, you should probably not use what this says, and 100% is pretty definitive. So what we will use here, we can now, based on this, I'm not very satisfied. Based on this, I'm actually thinking, not a good data set. Not a high chance to do anything. But why don't we do something? Okay. So I don't want to use neural networks because I already know I'm going to overfit. So I'm just going to choose a decision tree and then see if I at least can get that 2-to-1 generalization. So we press build, and then it actually builds our model based on all these parameters that it figured out. And as it built the model, we find something. Okay, so we find that, again, the best guess was 61.61. The good news is now we actually improved over this by building a model. We got to 80.24% accuracy. And that is actually sort of on the internally held out data set. So that is generalizing. And the generalization became a little bit better than predicted, which is always what we want because our predictions are always like lower limits or upper limits, depending on what it is. But you were always going to be either at that or better. And so it's a little better. It's 3-to-1. but so we get sort of 80.24% accuracy. And I mean, it's actually not so bad, because what it means is that it's better than just saying not survived. And also, we improved over the best guess by 18.63%. But the point here is, it's not so satisfying. We don't really know. It's like, what does this do, right? So what we can do is we can go back and say, okay, this all looked like it's going to be just very gooey anyway. So it ended up being gooey, right? Not great accuracy, not great generalization. It was like, okay. So what we can now do is we ask ourselves, well, if you look at all these parameters, really, what can a machine learner do with the name? What can a machine learner do with a random ticket number that isn't even normalized to anything, right? So the answer is not a lot. It doesn't contribute to solving the problem. Why would you random ticket number that's not even normalized contribute to whether you survived or not? I could see the gender, I could see the cabin class, all of these I could see contributing, but also the passenger ID, that's just a floating random number based on how the list was created. How would that contribute, right? I mean, it may for some random reason, but really it's not likely. So what we can now do is we say select suggested columns. So what this does is uses our attribute selection algorithm that we had in that we showed earlier, and then it selects only what it thinks contributes to the problem. And there's an actual question in the Q&A. Yes, can features be ranked by the relative utility? Is the answer is yes. So in the command line version, there actually is a ranking in terms of which one is the most important and the second important and the third important. Here in the GUI version, it's just picking them based on selecting. Hopefully that answers the question. Okay, so now, once we have selected those, what we do is we say remeasure. Let's see if those features that the system finds are actually better, right? So getting rid of stuff like the name, does this work? Well, and we can see it actually is, because right now we already see that there's a much higher generalization for the decision tree, 721 to 1, or it actually only needs one parameter. And this decision tree needs one branch. That's quite interesting. A neural network only needs 49 parameters, and it would also be an 18 to 1 generalization. So that's something. Now, is it more learnable? Well, it still has this GUI learning curve. It actually didn't even change at all. So that's okay. But the interesting part is the risk for overfitting now, and it makes sense because we don't have to remember names or anything anymore in our machine learner, is really low, especially with the decision tree. So now it's really clear we want a decision tree. So let's use a decision tree and build that thing again. Okay, so now we didn't improve a lot in accuracy. It's still 80.92%. But the interesting point is that, and again, we don't expect 100% accuracy for this, because unless we're just taking the table verbatim, we will have, basically, it would be weird to predict really 100%. And I'll go into this in a second. Why we would be able to predict by 100% accuracy. So now we see the generalization is 721. That's a really nice big generalization ratio. And it turns out the model capacity is really just 1 bit. So if you signed up, then you could have this button where it downloads the Python predictor, and you would see like the formula, which is just saying, if this, then survived; if that, then not survived, which is, the depth of a binary tree of 1 level, right? And so now what's interesting here is, so that predictor seems to be highly general and gives us about 80%. Now, why does it work? What are the features that actually mattered? And the interesting thing is, here we found out, passenger class, sex, so basically the gender, and then how many siblings and how many kids. And of course, if we now look into the history books, we know that it was women and children first off the boat. And of course, wealthy women and children first would be the other thing we have to add, because if your passenger class is low, that means you're in a first class passenger, then um, you were closer to the rescue boats, and also you would be have a lot more personnel to help you. And then second, if you had a lot of kids, then you would be prioritized. This was based on the policy. So that makes total sense. And if I was now building an insurance policy based on, let's say the next Titanic, and life insurance basically on what's your chance to survive, well, yeah, I would probably base that heavily on the family size and the wealth of the person. Now, let's not go into detail of how fair or unfair that is or something. It's just the history at this point. But what is also interesting is it is pretty clear that there were probably poor male that also survived, right? The sort of poor single male also survived. And that means that this criterion doesn't give you 100% accuracy, but it gives you sort of the accuracy that you expect from this, minus the noise. And then we understood now, and we could confirm with history, we understood now the features that actually matter for this task. You can actually go further and you could say, okay, but now I'm an insurer, okay? And as an insurer, I'm not able, because the law says I can't discriminate based on sex. And then the question is, okay, where do we go from here? So what you do is you remeasure. And we find out, okay, so now the decision tree needs a little more, but it's not so bad, right? The progression stays the same. But we can now rebuild the model again and just see what accuracy we get if we actually exclude the gender. Um, yeah, and that's what's expected. The gender is so important that obviously you don't improve a lot over your best guess anymore. So gender is the biggest feature, and it would show you if you use the command line tool in the ranking too that gender is the number one feature. But this allows you in a completely different way to sort of understand the data, which features to use, in what way things contribute, and do I need to collect more data, less data, where would I go? And of course, I chose the Titanic example in order to be able to sort of appeal to the historic knowledge that people have, because it just confirms sort of the measurements that come out here. Yeah. Any questions about this?
We actually do have a few questions in the Q&A channel, Gerald. So I'll start asking those. But I would encourage everyone who's attending that if you haven't asked a question yet, and if you have one, go ahead and type it into the Q&A channel, and we'll make sure Gerald can get to your question before we finish today. Raghu has a question. He says, I don't understand what you were saying about capacity progression. Can you please re-explain that part?
Yeah, so we use the standard example that we also brought into one-on-one webinar, which is take these two series of numbers, 2, 4, 6, 8. Okay, if you look at 2, 4, 6, 8, the next number is immediately 10 in your mind, or 12, and so on and so forth. Why? Because you extract the rule plus 2, or all even numbers. So that means 2, 4, 6, 8, 10. You extract the rule plus 2. And if I give you now 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, and so on, you'd say, stop, stop, stop. I already get it. It's plus 2. So it's not about there's no data like more data. It's about there's no data like having enough data to extract the rule. Now, the counterexample is if I give you something like 6513, that is the sort of the last 4 digits of my phone number, and it turns out that's a random number. You can't do anything with it. You can't generalize. You can't tell me what the next number is. If I give you 10,000, the other one you could say me 10,002. Here you can generalize. The only thing you can do with 6513 before you have the rule is to memorize. And now this is what the capacity progression actually looks at. What we do is we take sort of the number sequence, right? If you had 2, all you can do is memorize. If you 2, 4, you could still just only memorize, because there would be a lot of things that could come out of this. But if you have 2, 4, 6, you're getting closer. 2, 4, 6, 8, 2, 4, 6, 8, 10, you now know exactly it's plus 2. Now 2, 4, 6, 8, 10 means now all you need to store sort of in your parameters of the model is +2. That means you end up with a really, really short rule, right? So you basically flat up. And the more data I give you, it doesn't add more decision points because you made your decision. You know exactly what's going on. In the case of 6513, as I add numbers and don't figure out the rule, it would just linearly increase and it would just basically go up all the time. So what we want is convergence somewhere around the 40-80 line here, and where it goes flat, right? So it should go up a little bit and then hopefully just go flat. And now that's the theory. The practice is every data set is somewhere in between, and then you have to make a decision. Now, not every data set is yellow though, because these are very small data set in these example sets. So if you have a bigger data set, it's probably going to turn green pretty soon, but may not, right? Obviously, it's a matter of measurement. Hopefully that answers the question.
Thank you. Um, Kareem would like you to revisit memory equivalent capacity. He wasn't really clear on how that came up in today's demonstration.
So the memory equivalent capacity is basically the capacity that a neural network or decision tree or XGBoost or whatever you're using has needs to memorize any table of the size you put in. Okay, and so now we want to be below that because we don't want to memorize. We want to find the rule. Now, to make things easier, in the web GUI, we call this just learnability, and then we count the parameters. But the reality is, in the command line version, you get an actual memory equivalent capacity, which is not so far off because in a neural network, the way the networks we built, all of them are maximum efficient. That means they have a guaranteed 1 bit per parameter memory equivalent capacity. And what that means is 46 parameters is the same as 46 bits of memory equivalent capacity.
Okay. Um, we have an anonymous attendee who has a couple of questions. I'll try to feed these to you one at a time, Gerald.
Mm-hmm.
And I would encourage the anonymous attendee, if I don't quite interpret your questions correctly, just type in more in the Q&A channel and we'll get it right. So the first question is, what is the limit of classification states? I believe that means how many different output or target buckets are you allowed to work with when you're doing multi-class classification?
So we can have, so when you do classification, there's no limit. I mean, we tested 10,000s of classes. So that's not, there's actually no limit on the number of classes, if that's the question.
I think that's the question. We do have a recommendation for how much data to have per class, though, I believe. Isn't that
Yes.
correct?
So we want at least 100 instances per class. That's sort of our rule, because it becomes very hard to do anything with less than 100 instances per class.
Great. And then the same anonymous attendee has another question, which is, what is your plan for building models other than decision trees and neural networks?
We have this on the roadmap. We decided not to do this basically as of 1.0 release. We decided to do this later, and we will basically um, look at this based on customer demand, right? So basically, right now when we test our stuff, neural networks and decision trees seem to just cover 98% of the ground. It's just what it is. And of course, if we find that there's a niche where we need sort of XGBoost or where we need SVMs or something, we can just build those in.
Great. And then the final question from this attendee is, could you briefly discuss the performance in a very wide parameter set, such as the genomic data?
Yeah, so since we measure, we don't have any problem with oddly shaped tables, right? So we have 21, we worked with data where we had like 21,000 columns and then 85 patients, right? So that means 21,000 columns were the sort of the human genome expressions, and then 85 patients were 85 rows or 85 instances. And a normal machine learner, all it can do is overfit for this kind of stuff, or it takes forever to create a neural network that finally generalizes enough, hopefully doesn't overfit and all of this. We measure this out and we figure out which attributes matter, usually within minutes for a data set like that, if not seconds. And then we go from there. So it's a very different approach because we can measure, we don't have to build yet. We can build after we measure.
I would also encourage everyone who's interested in that question to go to our website and pull down the archived webinar on finding the needle in the haystack. We did this last Thursday and we discussed genomic data sets and how our software works on them and what our results look like in detail in that webinar. So that would be a good thing for you to watch retroactively. There are a couple more questions, so let's just keep going. Danielle says, your measure and build times seem really fast. Are you pre-computing them here just for the demonstration?
Absolutely not. There's no pre-computation. It's all live. So yeah, no, we're not pre-computing. Our tool is fast because we measure and we don't guess.
Got it. And then I see this question actually from two people, from both our anonymous attendee and from Robert. Um, Robert says, I didn't understand why certain features were selected and others weren't when you gave the demo. What was going on there? I think really what Robert's asking is, how does attribute selection work?
Yeah, so it basically works like this. We take this table and we basically assume, what if this table only had the target column and one other column? And then we iterate through those. We ask ourselves, does passenger ID versus survived give the best generalization? Does passenger class versus survived give the best generalization? Does name versus survived give the best generalization? So we iterate through them and then we pick one, the one that gives the best generalization. And then we say, okay, but can we add a second one? Does that improve the generalization? And then we add a second one. And then we ask ourselves, can we add a third one? Does that improve generalization? And we do so until generalization doesn't improve anymore. And then we just pick those. Now, it's important here, this goes for the most general solution. And often you may say, yeah, that's kind of nice if you get a super small classifier and it does pretty well, but I want more accuracy. If you want more accuracy, you would have to manually add features. And you could either do this in the web interface by just clicking on them, or in the command line, you can add a parameter. You could, for example, if our attribute ranking finds these three features are the most general, you could do that. But if you don't like this, then you say, okay, maybe don't use 3, don't use 5, don't use 6 features, and then these extra features we will add to allow those that contribute still that sort of um, reduce the generalization the least, but add accuracy, right? And so in the end, if you say rank all of basically take all, then of course you take all, but you can just incrementally add features to reduce your generalization in favor of accuracy.
Great. Thank you so much. Well, um, last call for questions in the Q&A channel. All right, I don't see anything else coming in. So Gerald, maybe we could go back to that very final slide.
Mm-hmm.
And I want to thank you all so much for coming today to Cortec 301. We're going to repeat live, not pre-recorded, the Cortec 101, 201, and 301 series starting next Tuesday. So if you would like to come back and interact with Gerald directly on the core technology, we're going to go through that whole series again every Tuesday for the next, I think it's 4 weeks, because we're taking a break the week of Thanksgiving. And this week, on Thursday, we're going to be doing a benefits and applications webinar about working with time series data. And some of the main application domains for that are fintech, market predictions, and that sort of thing, but also the development of wearable health care or medical devices. So if you're interested in that, we'll see you on Thursday. We'd really encourage you all to go over to the Brainome website and sign up for a free account so that you can try out the software, just like Gerald was using it today. And that's at the URL below. And I also want to encourage, especially the anonymous attendee who was asking a lot of questions today, but really anyone, If you would like to have a further conversation with us and need to get into a little more detail, we're very much interested in speaking with you. Just email us at support@brainome.com. Thank you all so much for coming today. And we're looking forward to seeing you at a future webinar and or in a one-on-one conversation. Thanks very much. Have a great day.